Welcome back to the Deep Dive. It is Thursday, February 19, 2026.
Great to be here.
And I really hope you are having a fantastic week so far. Today, we are going to do something a little bit different.
Yeah, a bit of a pivot from our usual approach.
Exactly. Usually we take a topic and we look at it from a distance. We look at the trends, the big picture. But today, we're zooming in. We're zooming all the way in to a specific job, a specific technology, and a specific moment in time that I think is, well, I think it's going to define the next decade of human productivity.
It is absolutely the topic that connects everything right now. You honestly cannot look at the global economy or the healthcare system or even the supply chain without running into this head-on.
We're talking about the rapid and, absolutely breathless evolution of robotics engineering.
It's moving so fast.
It really is. But before you tune out thinking, okay, I'm not a math whiz, I don't care about factory arms welding car doors, let me stop you right there. We are not talking about the robots of the 1990s.
Right. No.
We aren't talking about dumb machines that just repeat a motion until they break. We're talking about physical AI. We are talking about embodied intelligence.
And that is the key shift. It is the difference between a tool and a collaborator. It is no longer just a machine following a hard-coded script. It is intelligence, real, adaptive intelligence that actually has a body.
Intelligence with a body.
Exactly. It is software that can push back against the world, feel resistance, and make decisions in real time.
Software that pushes back. I love that image. We are looking at a massive shift in the global labor market that is happening right now in real time as we speak. And to help us navigate this, we have a stack of sources on the desk today that is honestly a goldmine. I spent all last night reading these and I just could not put them down.
It's a really comprehensive mix. We have the macro view and the micro view.
We do. We're going to dig into the Future of Jobs Report 2025 by the World Economic Forum, the WEF. That's our heavy hitter for the economic context.
Setting the stage.
Right. Then, to get practical, we have a breakdown of the 10 must-have skills for a robotics engineer in 2026. And that's from Ed Stellar.
Which is a fantastic breakdown.
It is. We also found this fascinating cutting-edge curriculum on physical AI and humanoid robotics, which is essentially the textbook for the engineers of tomorrow, the people who are studying right now. And because we know everyone wonders about the bottom line, we have the Robotics Engineer Salary Guide from Coursera.
So we've got the theory, the practice, the education, and the payout.
Exactly. So our mission today for this deep dive is to decode what it actually takes to build the machines of tomorrow.
We want to know how much it pays, obviously, but also why, and this was the biggest surprise for me, why soft skills might actually be the secret weapon in a hardware world.
That is a crucial point. We tend to think of robotics as pure math and cold metal, but the human element, communication, creativity, adaptability is becoming more important, not less. As the machines get smarter, the humans building them need to be more, well, human. Okay, let's unpack this. I want to start with the big picture, the macro view. We are looking at the Future of Jobs Report 2025 from the World Economic Forum. When I opened this report, the first thing that hit me was the sheer scale of the growth. What is the headline here regarding robotics?
The headline is essentially an explosion. The report identifies robotics engineers as one of the fastest growing roles in the entire global economy.
Wow.
Yeah, it isn't just creeping up the list, it is rocketing up. It's sitting right there alongside AI and machine learning specialists and big data specialists. It is the trifecta of the modern tech economy.
So it's not a niche career anymore. It's not just for people in white lab coats at secret research facilities.
Not at all. It's fundamental infrastructure. If you think about the internet boom in the late 90s or the mobile boom in the 2010s, this is the physical application boom. And what's fascinating is how the WEF describes the driver of this. They talk about something called the human-machine frontier.
The human-machine frontier. That sounds incredible. It sounds like we are exploring a new continent or a new planet. What exactly does that mean in the context of this report?
It refers to the division of labor. It's a way of measuring who does what in the economy. Currently, looking at the source context, about 47% of tasks across industries are performed by humans only. Purely manual or cognitive human work.
Okay.
About 22% are machine-only, so automated processes, and 30% are a combination where humans and machines work together. That's the baseline we're sitting on right now.
Okay, so humans are still doing the bulk of the solo work.
Yeah.
Almost half of all tasks are just us relying on our own hands and brains.
For now, but the projection, and this is where it gets really wild, is that by 2030, which is only 4 years away from where we sit today, This is going to split almost evenly.
Evenly.
Yes, the forecast is roughly 33% human only, 33% machine only, and 33% collaborative.
That is a massive shift in a very short amount of time. I mean, going from 22% machine only to 33%, that represents a huge amount of automation coming online. That's billions of hours of work shifting from people to hardware. I can hear the listeners thinking, you know, okay, does that mean I'm losing my job? Is this the end of human labor?
That is the natural reaction, right? Panic. We see numbers like that and we immediately think of replacement. But the expert analysis in the report is quite specific about this. This isn't just about replacement. It is about augmentation.
Augmentation.
Right. The report explicitly states that concerns about humans running out of things to do are misplaced.
How so? Because if a robot is doing 33% of the work, that's work I'm not doing. The math seems to imply less work for people.
Think about it in terms of productivity and capacity. The idea is that productivity is going to skyrocket because the machines are taking over the tasks that bottleneck human potential.
The bottlenecks.
Exactly. They are taking over the repetitive, the dangerous, the heavy lifting, or the high-precision tasks that humans aren't actually very good at. This allows humans to do well human things: complex problem-solving, emotional care, creative strategy, management. The economy grows and the demand for labor actually shifts rather than disappears.
So it's augmentation versus replacement. It's like having a superpower rather than being replaced by a superhero.
That's a really great analogy. Imagine a nurse. If a robot can handle the heavy lifting of moving a patient from a bed to a wheelchair, which, by the way, is the #1 cause of injury for nurses.
Oh, I didn't know that.
Yeah, it's a huge issue. So if a robot does that, the nurse isn't fired. The nurse now has more energy and time to administer medicine, talk to the patient, and manage their care plan. The robot augments the nurse's ability to do the job safely.
That makes total sense. It upgrades the job rather than removing it. Now, we are seeing this play out geographically in very interesting ways. The report highlights that robot installations are not evenly distributed. They are heavily concentrated.
Extremely concentrated. About 80% of all robot installations are in just 5 places.
80%.
80%. China, Japan, the United States, the Republic of Korea, and Germany.
That's a tight club. Basically, the traditional manufacturing powerhouses of the world.
But looking at the report, there are some specific country callouts that really caught my eye. The Republic of Korea, for instance.
The Republic of Korea is fascinating. The data shows that 83% of firms there plan to use technology to augment their workforce.
83%.
That is an overwhelming majority. It's not a fringe experiment there. It is the standard operating procedure. If you are a business in Korea and you aren't automating, you are effectively already out of business.
And then you have Italy. That one surprised me a little more.
Italy is interesting because they are expecting net job growth specifically in robotics engineers. It's seen as a major economic engine for them. And Turkey is another one where robotics engineers listed as a fastest growing job role.
So it's spreading. It is. It shows that this isn't just about the global superpowers. It's spreading to mid-sized economies that want to compete on the world stage.
So what is driving this?
Yeah.
Why now? I mean, we've had robots in car factories for 40 years. We've seen the robotic arms welding sparks in commercials since the 80s. Why is the curve shooting up so drastically right now?
There are 2 main drivers identified in the report, and they act like a pincer movement. First, the green transition.
The shift to renewables.
Exactly. Robotics is heavily tied to renewable energy. Think about installing solar panels. We need to install millions of acres of solar panels to meet global climate goals. Doing that by hand is slow and backbreaking. Robots can do it 24/7.
That makes sense.
Or think about maintaining wind turbines offshore. It's dangerous for a human to climb a turbine in the middle of the North Sea in a storm. It's routine for a drone or a climbing robot.
And electric vehicles too, right?
Right. EV production requires a level of precision and scale that absolutely demands automation. You cannot build the green infrastructure we need at the speed we need it without automation. Manual labor simply cannot scale fast enough to meet the climate goals. So if you care about the environment, you actually have to care about robotics.
That's a connection I hadn't fully made before reading this. I always thought of robots as very industrial and maybe not eco-friendly, but they are literally the builders of the eco-infrastructure.
Precisely. And the second driver is demographics. This is the why for places like East Asia and Europe. We have rapidly aging populations. There simply aren't enough young workers entering the workforce to care for the elderly or staff the factories.
This is the hollowing out of the workforce.
It is. In Japan, in Germany, and increasingly in China, the workforce is shrinking. So in that context, robots aren't taking jobs from young people. They are filling a vacuum left by retiring people.
They need automation just to keep the lights on and the care homes running.
Exactly. It's a necessity, not just a luxury or a cost-cutting measure. It's a survival strategy for these economies.
Okay, so the demand is clearly there. The why is clear. It's climate and it's demographics.
Mhm.
Let's pivot to the how. If I want to be the person building these machines, if I want to ride this wave, what do I need to know? We are looking at the Stellar list of 10 must-have skills and that physical AI textbook.
This is where we get into the engineer's toolkit. And let me tell you, it is a very heavy toolkit. It's not just a wrench and a screwdriver anymore. It's a mix of skills that would have been 3 completely different jobs 20 years ago.
Let's start with the code. Skill number 1 is advanced programming and software development. But there's a duality here that confuses people. The sources say you need Python, but you also need C++ mid.
Right, and this is the mind-body problem of robotics expressed in code. You really do need both, and you need to understand why they are completely different tools.
Okay, I know a little bit about coding. Python is usually associated with AI, right? It's the smart language.
Correct. Python is the dominant language for AI, machine learning, and rapid prototyping. If you want to train a neural network to recognize a coffee cup, or use a large language model to interpret a command like clean the kitchen, you are likely doing it in Python. It's flexible, it has massive libraries, and it's relatively easy to write. It's the brain. It handles the high-level cognition.
But then you have C++ code. That's the old school hardcore language. Why do we still need that? Why can't we just use Python for everything?
Because Python is slow in computing terms.
Slow.
Yes, it's an interpreted language, meaning the computer has to read it and translate it on the fly. C++ is the performance language. When you are controlling a robot arm that is moving at high speed right next to a human, or a self-driving car doing 70 miles per hour, you cannot afford a millisecond of lag while the computer thinks. You need that real-time control loop.
So if there's lag, the robot might crush something.
Exactly. Or it might miss the target, or lose its balance and fall over. C++ gives you direct hardware control where milliseconds matter. It handles the drivers, the motion planning, the reflexes. So think of it this way. Python is the brain thinking, I should pick that up, and C++ is the nervous system actually firing the muscles instantly to make it happen.
That is a perfect analogy.
Yeah.
You do not want your reflexes to lag.
You definitely don't. And beyond just the languages, Ed Steller talks about the architect mindset. It's not just writing code snippets, it's understanding modular design patterns. It's using version control like Git, because modern robotics is a team sport.
Right. You aren't building a robot alone in your garage.
Exactly. You have distributed teams working on different parts of the code vision, balance, navigation, and if you don't have that architecture discipline, the whole thing just breaks when you try to put it together.
Speaking of nervous systems, that leads us perfectly to the second core skill, ROS, the robot operating system.
Yes, ROS. If you are in robotics, you live and breathe ROS. It's the middleware. It connects the hardware, the motors, the cameras, the LiDAR to the algorithms that control them.
Middleware. That sounds like a translator.
It is. Imagine you have a camera from Sony, a motor from Maxon, and a computer from NVIDIA. They all speak completely different electronic languages. ROS is the universal translator that lets them talk to each other seamlessly.
But the sources are very specific about a shift here. They aren't just saying learn ROS, they are saying learn ROS too.
This is a critical distinction. Ed Steller and the textbook both emphasize ROS too. The original ROS was great for research and academia. It was built by Willow Garage back in the day, but it wasn't really built for industrial products. It had security issues. It wasn't truly real-time. It relied on a central master node. So if that master crashed, the whole robot died.
Oh, wow. So it was a prototype tool. Great for the lab, bad for the factory floor.
Exactly. ROS2 is built for the factory floor, for the road, for the hospital. It offers real-time performance, better security, and industrial-grade reliability. It's decentralized. If you are learning robotics in 2026, you strictly need to be looking at ROS2. If you put ROS1 on your resume today, you look like a historian.
And the terminology there, nodes, topics, services, actions, it sounds like a social network.
In a way it is. Those are the building blocks. A node might be the camera driver. Another node might be the motor controller. They talk to each other over topics. It's a message passing system that allows complex behaviors to emerge from completely separate parts. It's like a group chat for the robot's body
A
parts.
group chat.
Yeah, like, hey, I see an obstacle. Okay, I'll stop the wheels.
Okay, so we have the brain with Python, the reflexes with C++A, and the nervous system with ROS2. But a robot isn't just code. It has to exist in the physical world. It has mass. It takes up space.
And that brings us to skill 3, mechanical design and electronics. The body.
This is where I feel like the skill set becomes incredibly broad. You can't just be a coder sitting in a beanbag chair.
No, you have to be a true generalist. You need CAD skills, computer-aided design using tools like SolidWorks or Fusion 360. You need to be able to design the actual metal and plastic parts. You need to understand kinematics, forward and inverse kinematics.
And you break that down, kinematics. That sounds like high school physics coming back to haunt me.
It's just the geometry of motion. Forward kinematics is asking, if I move this motor 10 degrees and that elbow 20 degrees, where is my hand? That's relatively easy calculation.
Inverse.
Inverse kinematics is the hard part. That is, I want my hand to be at this specific coordinate in space to grab the cup. How do I move all 6 of my motors simultaneously to get it there without hitting the table and without hyperextending a joint?
That sounds like a nightmare to program.
That is mathematically very complex, especially to do it in real time, hundreds of times a second.
And then you add the electronics on top of the math.
Right. You have microcontrollers like Arduino or Raspberry Pi for low-level stuff, or more powerful ones like the NVIDIA Jetson for AI processing. You have actuators, battery management. It's a massive system.
It seems like a lot to juggle. I mean, you have the code, but you also have to make sure the thing doesn't fall over or just overheat and catch fire.
That is the banter you often hear between the disciplines in a robotics lab. The software engineer writes perfect code, but the mechanical engineer points out that the sensor is vibrating so much it can't see anything, or the battery gets too hot and shuts down the CPU.
The physical world is messy. Code is clean, but physics is dirty.
Exactly. The integration of sensors into the mechanical body, dealing with vibration, heat, dust, moisture, that is a major challenge. You cannot just code your way out of bad physics. If the arm is too heavy, the motor will burn out, no matter how good your Python script is.
So that's the hard skills. But there is a new frontier mentioned in the Physical AI and Humanoid Robotics textbook. This concept of physical AI and VLA.
This is where it gets really interesting. This is the absolute cutting edge. This is what differentiates 2026 robotics from 2020 robotics.
Define physical AI for us. How is it different from the AI on my phone?
The AI on your phone, or a chatbot like ChatGPT, deals with data. It takes text in, gives text out. It's disembodied. It lives in a server farm somewhere. It doesn't know what heavy feels like. It doesn't know what slippery implies.
It has no body.
Physical AI deals with the laws of physics. It's embodied intelligence. It's an AI that interacts with the real world, pushes back against gravity, deals with friction and mass. It learns through physical contact.
And VLA. I keep seeing this acronym everywhere in the research for this deep dive.
VLA stands for Vision Language Action. It is an advanced architecture that unifies 3 things that used to be totally separate.
Okay, let's go through them.
First, vision. The robot seeing the world through computer vision, LiDAR, depth sensing. Second, language, using large language models to interpret commands and context. And third, action, translating pick up the apple into exact motor torque and trajectory.
So in the old days, you'd have to code, move arm to XYZ coordinates, close gripper.
Right. And if the apple moved 2 inches to the left, the robot would just grab empty air. It was rigid. It was blind execution.
Now with VLA.
You just tell the robot, pick up the apple, or even just, I'm hungry, get me a snack. The vision system finds the apple. The language model understands that an apple is a snack, and the action model calculates the movement to grab it, regardless of exactly where it is. If the apple rolls off the table, the robot adjusts and reaches down.
It bridges the gap between natural language and physical motor control. It essentially gives the robot common sense about the physical world.
Exactly. It is a massive leap forward. It turns robots from pre-programmed tools into adaptive agents. You don't program them anymore. You task them.
That distinction, tasking versus programming, is huge. But the sources also mention simulation and digital twins. Why is that so important in this context?
Well, think about the cost. A high-end humanoid robot can cost $100,000 or more. And a VLA model is a neural network. It learns by trial and error.
If it learns by trial and error, and the error is, I punched a hole in the wall or I fell down the stairs.
That is a very expensive mistake and potentially dangerous. So we use simulators like Gazebo, Isaac Sim, or Unity Robotics. We create digital twins, exact virtual replicas of the robot and the environment. We can train the robot for millions of hours in the virtual matrix.
Literally like the Matrix
Uh,
or a flight simulator.
exactly. It can fail a billion times in the cloud, refining the action part of VLA before we ever download that brain into the physical body. It accelerates development exponentially because you can run 1,000 simulations at once.
And the textbook mentions that this curriculum is inspired by workflows at places like Tesla Bots, Figure AI, Apptronic, and Sanctuary AI.
Which completely confirms that the trend is moving toward the humanoid form factor.
It does, which makes total sense if you think about it. We built the world for humans. Stairs, door handles, tools, they're all designed for human hands and legs.
Right. If you want a general-purpose robot that can work in a factory and a home and a hospital, making it human-shaped is the most logical path. It fits into our infrastructure without us having to rebuild the entire building. You don't need to install ramps everywhere if the robot has legs.
Okay, so we have built this incredibly complex machine. It has a VLA brain, a ROS2 nervous system, and a carbon fiber body. But the WEF report throws a curveball. It ranks analytical thinking and creative thinking as the top skills. And it talks a lot about soft skills.
This is the transition from can you code to can you work. You can be an absolute wizard at C++XIs, but if you cannot communicate, you're going to really struggle in 2026.
Why is that? Why is robotics so dependent on soft skills compared to, say, traditional web development?
Because it is inherently interdisciplinary. We just talked about how you need mechanical, electrical, software, and AI skills. No one single person is an expert in all of that. You physically cannot be.
So you have to collaborate.
You have to. The software engineer must be able to talk to the mechanical engineer. Ed Steller quotes Michael Costa, the director of robotic systems at Neptune Medical. He says, aspiring robotics engineers should develop strengths outside their core discipline.
Meaning, if you're a coder, go learn how a gearbox works.
Exactly. And if you're a mechanical designer, go learn what a neural network actually does. If you stay in your silo, the robot simply won't work. You need to speak enough of the other person's language to solve the integration problems. You need empathy for their constraints.
The WEF list puts analytical thinking at number 1 and creative thinking at number 2. That creativity part is so interesting to me. We typically think of engineering as very rigid.
But robotics is about solving problems that have never been solved before. How do you make a robot walk over loose rubble without falling? How do you make a gripper that can pick up a raw egg without breaking it, but also wield a sledgehammer? There is no textbook for that yet. That requires immense creativity. You have to invent the solution from scratch.
And resilience, flexibility, and agility are on the list too.
Because the technology changes so unbelievably fast, the Ed Steller report mentions that continuous learning is non-negotiable. The field changes monthly. If you learned robotics 5 years ago and haven't updated your skills, you don't know VLA. You don't know ROS2. You're obsolete. You have to be agile enough to throw away your old knowledge and learn the new stuff constantly.
That's brutal, but obviously true. WEF says 85% of employers plan to prioritize upskilling, so they know their teams need to keep learning.
And here is a comforting stat from Ed Steller. 70% of skills are transferable between automatable and non-automatable work. So even as AI does more of the heavy lifting coding, your understanding of the system, your ability to solve complex problems, that remains incredibly valuable.
Let's talk about the darker side for a moment, or at least the riskier side. Segment 5 of our outline covers security and ethics in the machine age.
This is a huge component of both the Ed Steller and WEF reports. Cybersecurity in robotics is not just about data theft.
Right, if someone hacks my laptop, they steal my credit card numbers. It's bad, but nobody gets physically hurt.
But if someone hacks a manufacturing robot, they can swing a 500-pound arm into a person, or shut down a power plant, or sabotage a production line so it intentionally makes defective brakes for cars.
The risks are deeply physical.
They have physical safety risks, data integrity risks, and operational continuity risks. It's incredibly high stakes. You aren't just protecting data anymore, you are protecting life and limb.
And the WEF notes that geoeconomic fragmentation is driving demand for security roles.
That's the WEF's polite way of saying global conflict.
Right.
As the world becomes more divided politically, protecting your infrastructure, which is increasingly robotic infrastructure, becomes a matter of national security. Robots run the supply chain. If you can hack the robots, you can cripple an entire country's economy without firing a shot. So the demand for security-related robotics roles is naturally skyrocketing.
And that leads to safety protocols. We see ISO standards mentioned in the texts. ISO 10218, ISO 13482.
These are basically the Bibles of robot safety, and it works in a hierarchy. You start with mechanical safeguards fences, physical barriers, then electrical interlocks if the door opens. The power to the robot cuts instantly. Hardwired.
You don't trust the software for that.
Never trust the software for life safety if you can avoid it. Software can bug out. A physical switch is reliable. But then you have the third layer, which is software monitors. Code that explicitly checks the operational code. Am I moving too fast? Am I outside my allowed physical zone? If yes, trigger a stop. You absolutely need all three layers to be considered safe in this industry.
It's reassuring to know that these standards exist and are rigorously enforced. It's not just the Wild West out there on the factory floor.
Okay, let's get to the part everyone has been waiting for, the payoff. We're looking at the Robotics Engineer Salary Guide by Coursera.
The numbers are very strong.
Break it down for us. What is the median?
The median total salary for a robotics engineer in the U.S. is $140,000.
That's a very solid median. It is, and the range tells a compelling story of quick progression. Entry level, 0 to 1 year of experience, you are looking at $105,000. So you are hitting six figures almost immediately out of the gate.
That is strong.
Mid-level, 1 to 3 years, bumps up to $120,000. And senior, 4 to 6 years, hits that $140,000 plus mark easily.
But then you have the top companies.
The outliers. Google is listed with a MUIN of $253,000.
Wow.
That is a huge outlier, but it perfectly illustrates the premium paid for top-tier AI and robotics talent in big tech. They are aggressively fighting for the absolute best minds.
Johnson & Johnson is at $141,000. NASA JPL at $131,000. So medical and aerospace are solid, but tech is clearly where the explosive money is.
Generally, yes, but there was one piece of data in the top-paying cities list that I know you wanted to bring up. It's honestly my favorite statistic in the whole stack.
I have to bring it up. The list has the usual suspects. Cupertino, Berkeley, Redwood City, all Silicon Valley, all extremely expensive places to live. But then, sitting right there on the list is Nome, Alaska.
Nome, Alaska. Average salary, $131,002.
Why? Is there a secret underground robot base in the Arctic that we don't know about?
We can speculate, but based on the industry drivers we discussed earlier, energy and resources, it makes perfect sense. Oil and gas exploration, mining, maintaining automated systems on the North Slope or in incredibly extreme environments.
Right. If you need a robotics engineer to fix the autonomous pipeline inspection bot at 40 degrees below zero, you probably have to pay them a massive premium to actually live in Nome.
Exactly. It's a hazard pay premium combined with incredibly high technical skill. It's remote operations at its most extreme.
So if you want an adventure and a high salary, pack a parka and head to Nome.
Apparently so. You can be a robot cowboy out on the tundra.
And what about education? Do I need a PhD from MIT to get these jobs?
That is the good news. The data shows 65% have a bachelor's degree, 15% have an associate degree, only 13% have a master's.
That is so encouraging. It suggests that actual skills matter a lot more than just credentials.
It does. And the guide explicitly mentions that certificates in things like self-driving cars or C programming can drastically boost your salary. The field moves way too fast for traditional universities to keep up sometimes, so specific, updated certifications show employers you are current with the latest tech stack.
So bringing it all together, we have gone from the WEF predicting massive, massive growth to the nitty-gritty of ROS2 and VLA, to the soft skills of collaboration, and finally to the paycheck in Nome, Alaska.
It's been quite a journey.
If you had to synthesize this for the listener, what is the key takeaway? Who is the robotics engineer of 2026?
The robotics engineer of 2026 isn't just a mechanic, and they aren't just a coder. They are a bridge.
A bridge.
Yes. They are the bridge between the digital brain, that VLA, that AI, and the messy physical world. They are the ones who make the intelligence actually act. Without them, the AI is just a chatbot on a glowing screen. With them, it's a physical force that can change the real world.
That is a very powerful image.
And if we look at that final provocative thought from the sources, the WEF report mentions that by 2030, the split between human and machine tasks will be exactly equal 50-50.
Which raises the really big question.
If machines are doing half the work and physical AI is letting them think and move like us, are we designing our replacements? Or are we designing our ultimate collaborator?
Yeah, it is the question to ponder. Are we building the things that will make us obsolete, or the things that will finally let us do more than we ever dreamed possible?
I like to think it's the latter, but it really depends on how we build them and who builds them.
If you want to be one of the people building them, check out that Physical AI textbook. It sounds like the exact roadmap you need.
It certainly is.
Thanks for taking the deep dive with us.
Thank you.